Hello everyone, this is Meet Vyas and I am conducting small lecture series on quantum mechanics in which I am going to explain what actually the infinite square well potential is. Okay, so in the first lecture of this lecture series we will talk about what is infinite square well potential and time dependent and time independent Schrodinger equation. Here this two equation, time dependent and time independent Schrodinger equation, is very important topic because from this equation we can derive the energy eigenvalue and wave function of the particle which is confined between two potential barrier, and then we will move towards the uncertainty in the position and momentum of the particle which is confined between two potential barrier, and then we will move towards the solving the problems related to infinite square well potential. Now in this first lecture, let's get the answer of this question, what actually the infinite square well potential is. Okay, to understand infinite square well potential, we are going to consider this particular diagram in which I have shown three region 1, region 2 and region 3. Okay, so the concept is the region 2 is confined between two potential barrier of infinite value. Here you can see, so if there is any possibility that particle can exist in this whole system, it can be only in this region 2, because the region 2 has potential of zero value. In region 1 and region 3, particle cannot exist because of having infinite value of potential. Here we can understand this condition using this given condition where v is equal to 0 when x lies between 0 to L. So this condition is generally talking about this region 2 where the potential will be 0 and the potential will be infinite where x is less than or equal to 0. So this is talking about this particular region 1, and when x is greater than or equal to L, we will have the infinite value. So this condition is telling us about region 3. Okay, so finally we can conclude that the particle can exist only in this region 2 because of having the potential of 0 value. In region 1 and region 2 we will not have any particle because of potential of infinite value. Now let's talk about first how can we understand infinite square well potential using some example. Okay, so here we have considered the example of hydrogen atom from which we can understand what actually the infinite square well potential is. Okay, so here I have shown the hydrogen atom in which the electron is revolving around the nucleus. Okay, so here there will be two force acting on this electron. First one will be centrifugal force, which the direction of this force will be away from the nucleus, and another force will be acting on this charge will be the Coulomb force, which will be acting towards the nucleus. Okay, and these two force can be easily converted into potential by using the formula v is equal to minus integral of f dr. Okay, so we can conclude that we will have two potential barrier around this electron. So electron cannot move in this away from the nucleus or towards the nucleus, it will remain in this particular orbit. Okay, so this is the best example of infinite square well potential we can understand. Okay, now let's move towards the Schrodinger equation from which we are going to derive the value of energy eigenvalue and the wave function of the particle which is exist in region 2. Okay, so now let's talk about the Schrodinger equation. What is Schrodinger equation actually is? It is H psi is equal to E psi, where psi is the function of x and t. Okay, so here this is the time dependent Schrodinger equation, where the H is Hamiltonian and E is called energy eigenvalue. Okay, so but the problem is in region 2 we have potential which is time independent, so we have to consider here time independent Schrodinger equation. We cannot consider this equation because in this equation the psi is the function of x and t, and here we have potential which is not depend on time, so we have to consider Schrodinger equation which doesn't depend on the time. Okay, so now let's talk about the uh, procedure which is known as the separation of variable. In separation of variable, we can convert one function which is depend on two variable into two function which will depend on the different variable. Here we have psi of x and t, so we can convert this function into two function in which the one function will depend only on the position x and the phi which will only depend on the time. This phi of t we can write down as E is equal to minus I e t upon h cross. Okay, so finally we will get time time dependent Schrodinger equation as psi of xt is equal to psi of x e raised to minus I e t upon h cross. Now this is the wave function for the time dependent Schrodinger equation. So by putting the value of this psi of xt, we can get the time dependent Schrodinger equation. Here you can say this is the time dependent Schrodinger equation, where h psi of x e raised to minus I e t upon h cross is equal to e psi of x e raised to minus I e t upon h cross. Okay, but we have to consider here time independent Schrodinger equation, so we have to remove this particular value from the Schrodinger equation. So we will have finally the Schrodinger equation as h psi of x is equal to e psi of x. Okay, where the psi of x is known as the eigen function. We cannot call this function the wave function because it doesn't depend on time, so we will call this function as eigen function. Okay, now let's move towards the time independent Schrodinger equation, and from this equation we can derive the two values of the particle. First one is energy eigenvalue and second one is wave function. Okay, so here we have h psi is equal to E psi, where h is the total energy. We can take the h is equal to total energy when we have potential which is time independent. So here we will have H is equal to kinetic energy plus potential energy. Okay, and we already know that kinetic energy of moving particle is 1/2 mv square plus v of x, which shows the potential energy of the particle. Okay, now let's talk about the kinetic energy. Now we have to convert this kinetic energy into the function of momentum. So what we will do, we will multiply m in numerator and denominator by m. Okay, so we will get m square v square upon 2m plus v of x. So this, as we know that p is equal to mv. Okay, so we will get h is equal to p square by 2m plus v of x. So this is the value of Hamiltonian. So the from equation 3 and 4 we can write that p square by 2m plus v of x psi of x is equal to e psi of x. So this will be the time independent Schrodinger equation. Now we can further simplify by putting the value of the momentum. Here we have the value of momentum is P is equal to minus iota h cross del by del x. Okay, here, here we can consider momentum as the operator. Okay, in this quantum mechanics we consider the momentum and energy as the operator, because we cannot get the value of momentum and energy by using any kind of formula. So we have to operate this momentum and energy on particular state to get the answer. Okay, so we will consider this P as a momentum operator. Okay, so the value of P will be P is equal to IH cross del by del x. In 3 dimension we can also write as P is equal to minus IH cross into del, where del will be is equal to del by del x I cap plus del by del y j cap plus del by del z k cap. But here we are talking about one dimensional potential, so we need only del by del x. Okay, so we will consider P is equal to minus IH cross del by del x only. Okay, now let's talk about the putting this value of P in the equation number 5. So we will get minus IH cross del by del x of square into 1 upon 2m plus v of x sine of x is equal to e sine of x. And finally we will get, if we do the square of iota, we will get the plus I square, and what is the value of plus I square? It is minus 1. So here we will get minus 1 into h cross square upon 2m del square by del x square sine of x plus v of x sine of x is equal to e sine of x. So this will be the time independent Schrodinger equation of the particle. Okay, and here this equation is known as time independent Schrodinger equation, but this is not we want to derive for the region 2. For region 2 we have to do this potential is equal to 0. So for the region 2 we can get the equation is like minus h cross upon 2m del square by del x square sine of x is equal to e sine of x. So here you can see in region 2 we have considered potential as 0. So we will have, okay, we will have the time independent Schrodinger equation as minus h cross upon 2m del square upon del x square sine of x is equal to e sine of x. This whole term will be 0 because in region 2 we have potential is equal to 0. Okay.